Good morning, everyone. Welcome to the session on DIRAC brand KET notation. Before starting this particular topic, I would like to spend 1 or 2 minutes discussion on why we need DIRAC, BRA and KET notation. How it simplifies the mathematical representation of complex quantum system. As we know that in quantum computing, information is stored and processed using qubits. Here, qubit is like the very small unit to represent the state of a particular system. Unlike classical bits, in case of classical bits, as we already discussed in the previous videos, in the classical bits, the information is stored either in the form of like a 0 or 1. But whereas in case of qubits, it may available either in the 0 or 1 and both simultaneously. This phenomena is called as superposition. The existing of multiple states simultaneously is called as superposition, and that qubit can be represented as alpha 0 state. For example, I just mentioned like a single qubit which have the two states, base states, state 1 and state 0, and alpha comma beta are the probability amplitudes, and the state of psi is representing as alpha state 0 plus beta state 1, and the normalization condition, the probability conditions like alpha square plus beta square must be equivalent to 1. We also represent in a mathematical way. Here the state 0 is like a column matrix, column vector 1 0, and state 1 is taken as 0 1. Therefore, the state psi can be written as in a mathematical way alpha 1 0 beta 0 1. Here the alpha and beta are the probability amplitudes. When we multiply alpha 0 0 beta, then final the state psi is represented for the qubit, single qubit is alpha beta. In case of 2 qubit system point of view, in case of 2 qubit system, that is the system consists the 2 qubits, will have like a 2 power 2, that is 4 states, and it can be written as 0 0 state, 0 1 state, 1 0 state, 1 1 state, and this particular system can be written as alpha 0 0 plus beta 0 1, gamma 1 0 and delta 1. Here the alpha, beta, gamma, delta are the probability amplitudes, and you can write any constants, and the normalization condition like alpha square plus beta square plus gamma square and delta square must be equivalent to 1. This is the normalization condition. And we also discussed about the how to write the represent state 0 0 in mathematics way. So this is like a tensor product. So if you want to get the relation of 0 0 state of 2 qubit system, we need to take it as like a tensor product. So 0 is like 1 0 and tensor product with the another state of qubit like 1 0. Then 1 0 of 1, 1 into 1 1, 0 into 1 0, again 1 0 into 0, 1 0 0, 0 into 0 0. This is the way we can represent the states 0, 0. Similarly, we can write the states 1, 1 is like 0, 0, 0, 1. So by combining all these states, if you want to write it as like a psi, we'll get the matrix like column matrix like alpha, beta, gamma, delta, or etc. So this is the way we can represent the mathematical way for particular 2-qubit system. Similarly, if we have 3 qubits, if we have 3 qubits, then obviously we'll have like a 2 power 3 states, which is nothing but 8 states, and it is very complex to represent the psi 1 plus 2 plus 3 plus 4 plus the terms related to 5, 6, 7 and 8 terms, 8 states, 8 terms, and again the matrix is like 1, 2, 3, 4 like 8. So for single qubit system point of view, there is no much issue to write or to represent the states in terms of matrices or vectors. But when we are going for the higher qubit states, the representation and manipulating such large quantum states using ordinary matrices and vectors is very, very difficult. To simplify these representations and quantum operations, DIRAC proposed a compact mathematical language that is called as DIRAC, BRA and KET notation. See here, just I am giving the example related to the 2-qubit system. In case of written like ordinary mathematical way or in general way, alpha state 0, 0, beta state 0, 1, gamma state 1, 0, delta state 1, 1 and matrix like column, this much is there. Whereas in case of Dirac notation, simply this can be written as state psi. So just check the difference between the representation in ordinary condition, very like a huge process, and it is very complex. Even for the two qubit system, we need to write the different terms. If it has n terms, 2 power n states, so representation of that much in ordinary mathematics way, it is very difficult, and operations between the different qubit systems or the quantum operations representation is very difficult. That's what we are, that is the Dirac brand KET notation is a simplified and universal acceptable mathematical language of quantum mechanics. It simplifies the representation and manipulation of quantum states, especially for the complex multi-qubit system. Now, coming to the what is the exact meaning of Dirac and Bra KET notation. So first, I'll discuss about the meaning of KET. Here the word like KET. A quantum state generally will take it as like psi. This quantum state is expressed as a special type of vector that is called as KET. What if it is single qubit or the multi-qubit system? The state is expressed by using the KET. It is called as KET vector, which represent the quantum state. It is denoted by the symbol like this, is like a letter, whatever the letter you want to write. Here if you write psi, that it means that it is representing the KET of psi. If you write it as like a, that is nothing but KET A. If you are writing it as here, if you are writing it as A, then we can write as state vector A. If you write it as like a B, that is nothing but state vector B, or we can call it as KET A, KET B, KET psi, etc. So To distinguish between the different states, a label is inserted inside the KET like psi, A, B, etc. So here this is named it as KET A, this is named it as KET B, and this named it as KET psi. Now example point of view. Here I just mentioned it as state 0, KET 0 is called as 1 0 column matrix, and KET 1 is represented as 0 1. This is like just an example. KET forms the linear vector space. So the KET follows the condition like linear vector space. The meaning of linear vector space is if we have two states described by the KET A and KET B, then the linear combination like C1 of other constant, C1, C2 are take it as like a constant. C1 of A, C2 of B is a vector in the same vector space. These are like a non-zero complex numbers like C1, C2 are the non-zero complex numbers. Therefore, the KET follows the linear vector space. Just KET is nothing but it represents the quantum state. So it is used the symbol like this. If any letter is written here, then we can call it as KET of that particular letter. If I mention A here, then KET A. If mention B is here, KET B. Psi here, KET psi, and it follows the linear vector space. So KET is like a column kind of vector, and we can write it as column kind of matrix way. And coming to the bra, it's a bra vector, and it can be written as, see here, this is a symbol, in between there is a letter. So just difference, in case of KET, we'll write it as like this, and it reverse it. So that it means that the bra vector is a conjugate transpose of a KET vector. It is a conjugate transpose of a KET vector. I hope you know about the conjugate transpose. That means columns, like column is converted to the row, and the numbers are like a complex numbers is taken as conjugate complex numbers. Here, for example, if the KET A is taken as A1 and A2, then this is the KET A. How we can write it as like a bra A? I just mentioned it as like a complex conjugate transpose. Then it can be written as A1, that is column vector is changed to the row, and A1, A2 are the ordinary numbers. Now I am just take it as like a complex conjugate. Therefore, A1 star and A1 conjugate like a complex conjugate, A2 complex conjugate of A1 and A2. This is the representation of the bra vector. KET is just simply represent the state, and bra is like a conjugate transpose of a KET vector. So coming to the inner product. Inner product, that is what happened if you multiply both the state of KET and the bra. For example, I just mentioned it as KET A is taken as 1 I, and KET B is taken as 2 minus I. I want to take the inner product like A and B. See here, this is like bra, this is like KET. But in the given problem, we just have the KET A and KET B, but we are required of bra A. That's what. I just change the KET A to the bra A. As mentioned, it's a complex conjugate of transpose. Then column is converted into the row, So 1 is a real number, 1 conjugate is also 1, but I is a imaginary. The complex conjugate is taken as minus I. Now the B is like say 2 minus I. So I need to take it as the product between these two, like inner product. So I just mentioned it as 1 minus I, 2 minus I. 1 into 2, 2. And then I into I, that is I square, which is taken as like a 1. Then finally the value is like 3. So the product between the 1 minus I, 2 minus I is taken as 3. This is the answer. But here, whatever it is, whether it is minus 1 or so, here we'll get the answer like a scalar parameter. So the product between the inner product between the one bra and KET is always use the scalar values. But what happened if you take it as like outer product? Outer product between the bra and KET. So outer product is represented as this is the KET A and this is the bra B. Outer product combines a KET and bra to form a matrix. So inner product always gives the scalar, outer product gives the operator. I'll tell you that exact meaning, what is the meaning of operator. So it is written as like KET A, bra B. For example, here the KET A is taken as 1, 0 and bra B is taken as 0, 1. Sorry, here I am written 0, 1. Now the product between the KET A, bra B, which I take it as like 1, 0, 0. So this is like a multiplication which is gives like 0, 1, 0, 0. So that's what we need to know about the matrix multiplications, because in case of quantum operations we need to use the matrix multiplications, matrix addition, etc. So final conclusion, the KET represents the state, bra represents the complex conjugate transpose, complex conjugate transpose of KET, but inner product always gives the scalar, inner product, and representation is like this, it's a scalar value, and outer product is gives the operator. Here if you have any doubt relate to the operator, see here d by dx of sin x. What it means? It changes it as cos x. Here the function sin x is changed into the cos because of the operator, like a differential operator d by dx. So one state operator, that is one state is changed to the other state by operating with certain operator. So outer product is doing the same. If any particular state is operated by the outer product, that state is transformed into the another state. For example, if the outer product like AB is acting on the function state psi, then it may change into the state phi. So this is called as operator. And coming to the properties point of view, we need to mention it as properties. If psi 1, like a state psi 1, like a KET psi 1 and KET psi 2 are valid KET vector. If these two are like a valid KET vectors, the linear combination of them is also a valid KET. That is C1 psi 1 plus C2 psi 2 is also valid KET vector, and it can be written as KET psi. So this is called as linear superposition. That is, bra and KET follows the linear superposition principle. And similarly, the inner product between the bra vectors also follows the linear superposition principle. The inner product between a bra and KET is also linear. That is, for example, state psi on C1 phi 1 plus C2 phi 2. So this is the KET, this is the bra of psi 1 wave function state. This is like another linear superposition of the KET. So the product between these two, the inner product also a linear. For example, C1, then you turn into the psi phi 1 plus C2 psi phi 2. So it also follows the linear superposition, or it is a linear, the inner product is linear. Similarly, outer product is also linear.